last invited talk of the workshop from Xiang, and it's my great pleasure to introduce him. If you can share your screen now, and I'll do the introduction while you're trying to do that. So Xiang is the assistant professor at the CS department of USC, a research team lead at USC ISI, and also the PI of Intelligence and Knowledge Discovery Lab. He has received many awards, including NSF Career Award, the Web Conference Best Paper Runner-Up, ACM CKD Doctorate Dissertation Award, and several research awards from Google, Amazon, JP Morgan, Sony, and Snapchat. So he worked on knowledge acquisition and reasoning in NLP. He also has mentioned a bit in the panel discussion already. So without further ado, let's welcome Xiang and take
Thanks for having me.
Thanks for.
Can I see my screen? Cool.
Yes.
Awesome. Yeah, thanks. So I'm gonna share some thoughts that we learned in the past year or so about how to push this common sense reasoning capability really to more like a realistic use cases, or like what we call in the wild. And this is joint work done by my amazing students, Bill, who is also here as the part of the co-organizers, and Pei, Qingyuan, Jay, and my other collaborators, Yejing, Chanjar, and Wilden Cohen. Great. Let me start with scenarios that probably many of you have been seeing here. You're working on some research benchmarks for your little problems or the task of interest. And the next stage, you find out, oh, on the leaderboard, there seems to be some superhuman performance created by these like gigantic models. And you just start kind of wondering whether you should switch your thesis topic to work on something else. And at the same time, your friends in the industry start talking to you and ask like, hey, I see you guys making really good progress on these problems. And do you want to try on some of our data streams or data sets that we have in our systems? And then you start doing something with it, and since the data distribution or other kind of characteristics of the problems change a little bit, and you find out your system not really working well, and you just start kind of thinking about, is this really the right way to approach the problem? Right, let's break this down a little bit more, and we'll find out that kind of the practices or the research activities we've seen a lot these days are more like in the narrow AI paradigms, where you really try to perform well on some specific benchmarks, which means like your solutions is more likely customized for this narrower task, and you have a specific data distributions that you collect to represent this problem. And you have this like ID partition to create this training set and the depth set and the evaluation set, and then you're trying to quantify your progress in this paradigm. And it's likely that in this way, your solution will be hard to deal with these unseen situations, which is outside of your data distribution, and will be struggling with some even more like a vague or ambiguous inputs, which are not represented in your current collections of data, right? And what we are really after, I believe many of you are sure the same ambitions here, is trying to make the system perform well in the real world or in the wild. That means like you really want to build a system that trains on some data, but it turns out to be applicable to a wide range of tasks that are out of the training distribution, and generalize well to the novel setting, and can handle more noisier and ambiguous input. So that also translates into things like you want a system to generalize unseen cases, but also robust to the input perturbations, and can have a pretty good data efficiency, which means like train faster with less or fewer training data points. And it's really doing what we expect the system to do, meaning fairness and trustworthiness. So there's clearly a war right now going from narrow to the more general AI, which is what we are trying hard to do. And my personal take here is like, we think common sense reasoning is really a possible one of the useful capabilities that can try to break this war even just a little bit. And the reason is being that seems like we know common sense is trying to capture human-like ability to understand and generate everyday situations, events, and other scenarios. So it actually provides a And like ideally, it provides like designable inductive bias for the machine to generalize to this rural setting. Among many of the other hypotheses of the models that you could possibly have when you randomly initialize your model parameter and optimize it with gradient descents using some training data sets. There could be many ways you can go wrong, but hopefully with Commonsense injected in a certain way, which is what exactly the way are still open questions for sure, but hopefully we can narrow down the search space a little bit to some solution points that we more desire to see. However, the way we are approaching common sense reasoning right now is also a little bit to data set or benchmark focusing. We're seeing very good progress by training more powerful language model, injecting or retrieving supported corpus or knowledge to augment the language model. We're making very good numbers on the sheet, right? But at the same time, we also found out there's too many things being overlooked. For example, many of the data sets we've been playing in the past 2 years or so are kind of focusing on discriminative or close-ended reasoning, which are not a bad thing because it's more constrained, it's easier to evaluate. You can trust your evaluation metrics more than just doing free text generations, which we not yet have a very kind of a reliable evaluation protocol yet. But that's definitely something we should think about. And these data sets are more like having a static partition of training, dev, and test set with even the IID distribution between these two, between these three. There's not much notion of evaluating the system's performance when you are operating on logically equivalent or semantically equivalent, but linguistically different kind of perturbations of the input and output data points, right? So that part is still kind of missing in many of the evaluation work been done in the past year or so. And we are also not really looking at how these systems can quickly generalize or adapt to unseen task formats at the test time. For example, we know that as human learns, they learn progressively, continually over a curriculum of a task, maybe from easier or more basic ones to more advanced and more compositional ones. And this kind of the notion of making evaluating the progress wasn't much seen in the current literature as well. So regarding these issues, in this talk, I'm trying to just address maybe a tiny bit of the surface of it and trying to show you how we are considering these limitations of how we evaluating the progress of common sense reasoning and trying to propose some newer formulations of the common sense reasoning challenges and share with you the evaluation protocols we've been doing here and hope to get some feedback and some new thoughts from the community. So first thing we are pitching here is we think that we should go beyond discriminative reasoning to more like testing the system in terms of open-ended reasoning. That means like going away from binary or multi-choice QA to more like generative or retrieval-based type of reasoning process for evaluation. And also we want to really test the system's robustness in terms of making logically consistent predictions. And we also want to look at the system's ability of learning from a bunch of upstream tasks that have a different formats, but also learn to generalize either in zero shot or in a few shot manner to some unseen task formats or domains and so on. So let me start with the this like open-ended reasoning first. So the first work I'm going to talk about is done by my amazing collaborator students, including Bill here, on making a generative common sense reasoning problems as an example of constrained text generation. So we know, again, too much work focusing on discriminative reasoning. We see a lot of, I mean, I'm not talking down of any of this work. They are really helping we build up the community and getting people interested in working on the problem and making good progress. But it's just that there's some caveat we should think about when working on and when interpreting the high numbers we get on this data set. One of them I personally think is that pre-trained language model, the way that mask language model works is trying to mask out some spans from the text and trying to make the model to predict them. And if you think about a special case like a salient span masking, they're just focusing on looking at some noun phrase chunks or verb phrase chunks in the text and try to recover them. And this actually aligns pretty well with these discriminated reasoning benchmarks, where you actually look at an answer span that is most likely to go after the question sentence or be plugging into the closed style question sentence to make a plausible statement. And this is actually what the MLM is trying to do by looking at a lot of corpus. Sometimes you don't even know what are the corpus they are using if those are not public. So there's a risk that the numbers we see in here is overestimated, and it's because of certain data leakage that we are not fully aware of. So I just feel like we should be careful in terms of interpreting the high number we got. And at the same time, we can also think about moving away from this discriminated reasoning process to think about how to generate sentences that are making common sense to human, and use that as a proxy of evaluating the progress. That's kind of the motivation behind CommonGen. We try to simulate a very simple task where you give human a list of words or phrases, and these words could be just nouns for objects and verbs for actions that humans will commonly encounter in their daily life situations, like dog, frisbee, catch, throw. And what we asked the system to do is trying to compose a sentence using all of these words, where the sentence is describing a plausible scene in your daily life, right? In this case, if I show you some of the sentences that we collected from the human annotator, there will be like, a dog leaps to catch a thrown frisbee. The dog catches the frisbee where the boy throws it, and a man throws away his dog's favorite frisbee, expecting him to catch it in the air. People can be very creative. They can make many versions of these kind of sentences, but all of them are really describing some plausible things we will encounter. Versus you won't see sentence like a dog throw a frisbee to a man, right? And then the man catch the frisbee in the air. Things like that will be less likely to come up in our daily life, right? So, but technically, we think this is also a very interesting problem because of two reasons. One is that rather than just giving the systems, giving the NLP, natural language generation systems, the possible shortcuts to learn between the given concepts and the target sentences, where you just need to learn some co-occurrence patterns between these concepts in order to fit the scores like Blue 1 or Rouge 1 very well. We actually ask the system to really understand what are the plausible relationships between these concepts in order to really create sentences that can get a high plausibility score, which I'm going to elaborate how we evaluate the plausibility scores in a little bit later. But here as an example, if you are given concepts like exercise, rope, war, tie, and wave, what we hope the system are doing internally is to understand that exercise will lead to releasing of energy, and the rope can be used for tying something, and releasing energy can is led by having some motions on your body, and wave is a type of motion people can do, and the rope is used for doing the waving action. And then at the end of the day is like, you will see that the motion will cost more energy if the rope are tied to a wall. All of these together are very useful step-by-step reasoning kind of knowledge to lead to the final generated sentence, which is like a woman in a gym exercised by waving ropes tied to a wall. right? Instead of saying like you are actually tying the rope to the wall, and by doing waving of your body as an exercise, as another alternative sentence of composing, composed by the same set of words, right? And in fact, when we're creating these data sets, by curating this set of concepts, we keep in mind that we try to diversify the type of knowledges that might be possibly used to tie these concepts together. So we look into spatial knowledge, object properties, human behavior, temporal knowledge, and some other general ones. The second thing we're pretty interested in thinking about is the compositional generalization, which is like we're trying to remove any possible shortcuts the system can learn during training by just knowing, oh, I should put apple and bag and put these three words together in a certain way by looking at this training sentence. Actually, our test sets always have novel compositions of these concepts that's been seen in the training phase. So things like peer, basket, pick, put, tree, these kind of 5-word compositions was never seen in the training phase, but you might see basket in some other training concept sets and put in some other concept sets. So we do enforce the system to learn how to interpret individual concepts and how to relate these concepts together with plausible relations and make sentence out of these novel compositions of concept. Cool. So this is pretty much the problem formulations I just described. And the interesting thing I want to show here is like how really these existing systems, including CommonGen text sequence to sequence model, as well as this text autoregressive language models and text to text language models are performing on this problem, right? So in this example, you have 4 given concepts, which are hand, sink, wash, and soap. And the interesting thing we first noticed is that almost all of these systems, they can successfully learn to use all of the concepts in composing a sentence. For the, I mean, this is a hard constraint for only one of the system, which is the third one that comes, but they are not used as a hard constraint in any of the remaining systems. So for example, BART and T5, they do learn during the training phase to copy these concepts in producing sentence. That's the first thing we found out, that it's not too hard to let the system to learn. You have to use the concept. And second thing is, you will find out that most of these sentences showing here on upper prop generated by the machines, they are grammatically correct mostly. Like you wouldn't be using, you wouldn't, I mean, the system wouldn't mistakenly use the nouns in the position where the verb's supposed to show up, right? For example, Bart is giving like a man is washing his hand in the sink with soap and washing them with hand soap, which are pretty good sentence. And T5 says like hand wash with soap in the sink. And some other less plausible sentence might be like a hand works in the sink, which are also a grammatically correct sentence, like the first one upper there, right? So and versus what human written for the same set of concepts will be like a girl is washing her hands with soap in the bathroom sink, or like I will wash each hand thoroughly with soap while at the sink, and the child wash his hands in the sink with soap. So it's a little bit hard to really distinguish, let's say, human written sentence if I'm versus like say sentence generated by BART or T5 in this case, in this particular example. So the first thing we notice is just like the system works not bad, actually much better than I expected. So we did some more like quantitative evaluations, starting from having some initial observation of these case studies. So what we actually compare here are 2 groups of methods. The upper part is this non-pre-trained sequence-to-sequence model. 2 of them are using concepts as hard constraints. So the decoding process has to include these concepts in the output. and the lower part are a lot of pre-trained language models that you probably are familiar with, like UDLM, BART, and T5. So basically, one interesting thing is to see here is like whether the pre-training is actually injecting useful knowledge for the system. And it turns out the answer is yes. You can see that lower part of the systems generally much better than the upper part of the system. Another thing I want to point out in this table is about the metrics. So you are looking at 6 columns of metrics here. The last one is the coverage, which means like whether the system actually used the concepts that are given in their output. And turns out that, like I said before, most of the systems are able to learn to use these concepts in composing the sentences, even they are not asked, even they are not imposed as a hard constraint. And one kind of takeaway here is like we have actually conducted some correlation analysis about which metrics aligns better with human judgments. And turns out that the SPICE metrics, which is looking at the argument and predicate roles of the words and see if that aligns with the Go references. And that actually captures a better correlations with human judgment. And that's the main thing we were looking at in these data sets. And it turns out that the T5 large is giving the best numbers there, which is 31.6. But again, if you all look at these numbers compared with the human performance, there's still a larger gap to catch here. So that's kind of the where we are when we publish the paper. And then almost like a year later, if we're looking at the leaderboard right now, we see people making some progresses, right? Like by still building ideas on top of these T5 large language models. But in addition to that, they start trying to retrieve relevant sentences to those given concept sets to augment the context when generating things, or they try to look for some knowledge graph triples or other kind of a prototypes they can think of to augment the generation process. And the numbers sort of increase from 31 to like 33 or close to 34 for the SPICE metrics. But it turns out there's still a long way to go. And we're looking forward to your contribution to this challenge as well. Any questions for this part so far? Great. Cool. And we also, after working out these CommonGen data sets, I think one of the most common questions I got asked is like whether the evaluation, the automatic evaluations are easy to be done, or like is it actually reliable by looking at just this a few metrics like SPICE. So that also kind of let us rethink about maybe we don't want to make one step that is too far away from what we actually are confident at in terms of the evaluation. So a follow-up efforts, which is also done by Bill, is to look into answering questions, but not with this like closed set of answer choice. Rather, it goes into a more like open-ended answer choice ranking paradigm. So I'm using this like a global warming examples here to walk you through what this challenge looks like briefly. If you get asked about like what can help alleviate global warming in the kind of a previous multi-choice common sense reasoning data sets, it's likely I'm gonna create 5 different or 4 different candidate answers for you to choose from. But now in the open-ended common sense reasoning, when you're given a question, what you actually provided to search from is a large text corpus of common sense facts. In our case, we used the generic KB, was done by Peter Clark's group in AI2. And basically, most of the time, every sentence in this corpus is describing some common sense or war knowledge about a few concepts. For example, carbon dioxide is the major greenhouse gas contributing to global warming. or like the tree removes carbon dioxide from the atmosphere through photosynthesis. And we actually looking to see people build up systems that can go around these pieces of fact statements, chain them together in a certain way such that they can find out that, oh, tree is actually a good mean of reducing carbon dioxide, and such that you can use that to answer the question, right? For example, at the end of the day, we are asking you to rank all of the concept, words, and phrases in terms of the plausibility of answering this particular question. And hopefully we see tree is ranking on the top places, maybe close to renewable energy. And also we want you to provide with us the specific chain of statements that you are used to lead to this answer. So we are also looking for interpretability in terms of how the decision is made by the system. Yep, so that's a good effort in terms of making the evaluation a little bit easier, because you can trust these ranking-based evaluation metrics like MRR and precision record at K in a better way than the evaluations for the free text generation. Cool. The next work I want to talk about is a little bit switching the gear, which I want to motivate it from the human communication that of course require some common sense, especially social common sense. And I want to motivate why we are looking for more logically robust reasoning capability, and how to really evaluate that capability in this context, right? So think about if you are just receiving a message from your friend who tells you that your friend is going to perform in front of thousands tomorrow, maybe on a piano competition. So the explicit knowledge behind these text messages that your friend is going to perform in front of many people tomorrow, and a relevant inference rule you might pop up on top of your head is performing in front of people can cause anxiety, right? Because of causing anxiety, so you would make an inference that you would try to calm your friend because of the anxiety caused before your friend's competition. So you text back with the sentence like, deep breath, you will do great, right? This is very kind of a common and commonly seen kind of a reasoning process. But the difficult part, if you want to build such a inference process using current NLP model, is that there's so many ways you can express this same common sense axiom, right? You can say like a person performing in front of people might be nervous, or people performing in front of people find it harder to be relaxed, or like it can be harder for someone to be calm when they're about to perform. So with the same underneath common sense axioms, there's so many linguistic variations you can create to express the same message. And can the machine systems really digest all of these variations of the common sense statements in the same way, in a consistent way? That's basically what this project was asking about at the starting point. So we know that inference making require this implicit common sense reasoning, but human fluidly adapt to diverse linguistic expressions. Can machine also do the same thing? That was the motivation for we doing this RICA effort, which is trying to evaluating the robust inference capability by designing common sense axioms and turn these common sense axioms into linguistically diverse statements in a almost like an automatic way with a little bit human in the loop kind of a system. So I'm just kind of trying to do a brief overview of what this process of creating this challenge looks like. We start with some primitive of logical reasoning, which is like just primitives like predicates like accessing the property of a certain entity, or like looking at the relations R between two entities A and B, or like comparing the values X and Y, right? And then you can start manually write down some logical templates. Like if I know A and B have a relation R, would that lead to the conclusion that A's value P is with a certain comparison to B's value P, right? And then I can start automatically fill up these logical templates by retrieving property values of different entities and relations values between different entities from an existing knowledge graph like Commonsense. Right, so I can start having more concrete logical axioms like if A is B's lawyer, like AB with a relation lawyer, then what will be the comparisons between A's knowledge versus B's knowledge, right? So with these more concrete axioms, I can start creating specific natural language statements grounded to these axioms. But I will start doing many perturbations that I ask to do. For example, I can paraphrase the relations. I can perturb the positions of A and B. I can do some double negations, things like that. So at the end of the day, for this one instance, I can create a bunch of linguistically diverse common sense statements like A is B's lawyer, so A is more knowledgeable about law than B, or like A is B's lawyer, so A is less clueless about law than B, or like B is less informed on the law than A, right? And one more step we did is, in order to give the language model the chance of memorizing data about its entities, so we start creating fake entities, or what we call novel entities. So A is actually instantiated by some random name generators that are not corresponding to any real like English names in this case. So with these common sense statements, the challenge is basically trying to ask the system to give consistent judgment on these common sense statements across all of the different linguistic perturbation or variations of the same axiom, right? So if a system can give the same answers to all of these 10 or 5 different statements, we think it's more likely to perform a robust logical reasoning. If the system giving quite divided and mixed answers to these statements, we think they are still a gap to fill up here, right? So with that, we look at basically how the system perform. So what we're showing here is basically the average accuracy of different systems on different subsets of the common sense statements I just described. There's a subset where you can train with a lot of training data, or a moderate amount of training data, or not using any training data to fine-tune the model. And we test these systems' performance on the same test set, which are curated by human, which are human-written common sense statements. And we also ask them to manually provide multiple linguistic variations of the same statements in our turking process. So if you pass these test sets to human to make judgment, they can have a 91.7% accuracy. But if you test the state-of-the-art language models, large bird large, robot large, some knowledge augmented models like Ernie, and some text-to-text transformers like BART, it turns out that they are still perform like a random guessing type of behavior, which means like there's not really a consistent prediction patterns among different variations of the same common sense axiom. And we actually replace back real English names to replace the novel entities that we create, and it doesn't really change the conclusions here. And maybe you will be wondering like whether we are too harsh to these systems, like in terms of allowing them to fine tune or not, right? So we did try giving them more fine tuning data in terms of learning what the task is really asking them to do. So you can see the x-axis here is the amount of training examples we give it, and the y-axis again, the task accuracy. And we have 3 different test sets here. The bottom one, the red one, is again the same test set as the left-hand side, which is a human curated set. So you can see the system don't really get away from a random guessing with more training data, versus on some other more like automatically created test sets, like with human verification. The numbers seem to improve, but I think the caveat here is like in this automatically created test sets, there are some patterns can be learned from a training set. So with more fine-tuning data, indeed the system memorizes some good shortcuts, and those shortcuts seems to work well on this automatically created test set or human verified test set. But again, I think what we observe on the human curated set is still telling that there's a lot to do with making this state-of-the-art language model to be having robust logical reasoning capability. Any questions about this part? Please let me know if I'm good at the time. I think I'm already out of time, right? Cool. I guess I would just go quickly for the last part. So like I said, the last thing we're really interested in knowing is this cross-task generalization, where we do want a system to be able to generalize to some unseen task format, and also in a very data efficient way, right? So like if you make a look at analogies to what human learn is like when they really learn to do calculus, they won't learn that as a baby. They will start learning some basics like about math and geographic and chemistry in high school, and then at a certain time they will start really picking up calculus because of they do have the background knowledge of other things. So basically we ask the question to the machines like whether they can acquire these better generalizable reasoning skills and task solving skills in the upstream training phase, and apply those skills to help them learn faster on those out of distribution task and unseen task format, right? And this is the work done by Qingyuan and Biu called CrossFit. So the pipeline is basically, if you look at what people have been doing right now, you have a large scale for training going on to get a checkpoint, and then you take a downstream task training data into fine tuning, you got a final model to do evaluation on an out of distribution test set. And in CrossFit setting, we have an additional step where you go from a pre-trained checkpoint, you look at a bunch of upstream learning tasks, you get a new checkpoint by learning from those upstream tasks, but you then ask the model to do downstream fine-tuning on an unseen task with very few amount of data, maybe just a handful of them, and you see how this model is generalizing to that unseen target task, right? So the interesting contribution of CrossFit is actually we look at a whole, a pretty comprehensive range of tasks and creating a task ontology for them, right? So we consider 160 data sets, and these data sets are organized into a 3-level hierarchy where like if you have reading comprehension, have a bunch of data sets, and multi-choice QA have a bunch of data sets. And all of these QA data sets belongs to their parent node, which is the QA node. And it's on contrast, you have this classification and conditional generation and other tasks altogether. So with this tax ontology, the interesting thing is you can partition these data sets in many different ways. You can say, I want to look at if the system can learn from classification and generalize to QA, which they never train on QA. Or you can ask if the system can be trained on reading comprehension, but never train on multi-choice QA, whether they can generalize to multi-choice QA and so on, right? So the question, I'm not gonna show all the analysis we have, but I just want to have 2 takeaways here. One takeaway is, does the upstream learning help the cross-task generalization? And the way we did that is to just train the model on upstream data sets using either a multitask learning strategies or a meta learning strategies. and then just take these two model checkpoints and then do fine tuning on different downstream tasks and see how these downstream, how these upstream chaining are improving the downstream performance. And an interesting thing I want to point out is we don't report the absolute performance, but rather we report the relative performance gain on top of the direct fine-tuning baseline. So all the bars here you see, if they are larger than 0, it means that they improve by a certain percentage over the direct fine-tuning baselines. If they are negative, that means they have decreased performance compared to the direct fine-tuning baseline. And on the rightmost side, you can see this bunch of green bars, and those are the average performance or across all of the downstream tasks. And you see they're all positive and actually close to or higher than 25%, meaning that all of these algorithms we are listing here for upstream learning, they all seem to be helpful for the model to learn some generalizable skills to help them improve over direct fine-tuning baseline. And the second takeaway is whether certain upstream tasks are more helpful than the other upstream tasks. So in this case, we look at maybe for classification, whether non-classification tasks can actually help. And the finding is that, interestingly, classification tasks and non-classification tasks seems to be equivalently helpful in this case. But again, I think there's still many open questions for the analysis here. And I feel like our understanding of the task may not align fully with how model actually learn these transferable skills. That means the task ontology we are creating here might not be solely aligned with what the system think are the right way of categorizing the reasoning skills and task skills. So with that, I want to just conclude the talk. And I think the one thing I want to advocate and serve as a takeaway is it's pretty exciting to look at many more ways of evaluating how a system solve a problem than just looking at how a system solve benchmark data sets. You can think about data efficiency, you can think about fairness and trustworthiness, and you think about robust to perturbation and generalization to unseen tasks. And I hope that could kind of influence the community's ways of build up their evaluation protocols in the future. Thanks. So
Thank you so much for the fruitful talk. It has a lot of interesting things from multiple dimensions. So yeah, thank you. I don't know if you have time for questions or.
We're a little bit behind schedule, but I mean, for everyone here, I think we can just have a few minutes of questions and then move on to the closing remarks.
Yeah. I mean, I'm totally fine with like skipping my QA. I think I'm taking too much time, but just text me. I mean, put question on chat box or email me if you have any suggestions or feedbacks. I think that's what we really will be grateful about.
Yeah, that's a good idea.